When we talk about sustainable energy or renewable energy, it is impossible not to talk about solar energy or solar power. And as we know, the sun is the ultimate source of energy on Earth, and it's considered as an unlimited source of renewable energy. So it supports the life on Earth, and without it, we can say that the world will be a frozen wasteland of ice-covered rock. So we need the sun to support our life on Earth, and even for the supporting or the effect on weather and climate changes as well. So we know that the sun has a lot of energy, and we understand that harnessing this energy would be quite beneficial towards us because we can have a free form of energy that is always there. But the question is, how do we harness efficiently this energy that is coming from the sun? So in order to understand the mechanism on how to harness this energy, not only harnessing as a form of heat or into electricity, we need to understand first some of the basic aspects like the various characteristics of the solar radiation. So let's start from that. So the sun is basically a very big ball of fire. It's like a mass of constant nuclear activity. And so this is a very hot mass. It has around 5,000 degrees Celsius of surface temperature here and around 15 million degrees Celsius at the core of the sun. So it's a nuclear core. And so because of this very hot temperature and the size of the sun is around 300,000 times bigger than the Earth, it emanates a lot of solar radiation. And the solar radiation is in the form of electromagnetic radiation. So when we say electromagnetic radiation, it's like some waves of light and heat that is coming towards the Earth. So this solar radiation spectrum at the Earth's surface, we can look at this diagram here. So this is the spectrum that is emanating from the sun that is absorbed by the Earth. So we have the solar irradiance at the y-axis, which is the watts per square meter, so the amount of power per unit area, and this is the wavelength of the solar light. So the radiation can be divided into three sections of the wavelength. So we have the UV light here, which is the shortest wavelength. So this is ultraviolet light, and we have the visible light, wherein this is the section that we can actually see, and the infrared light are the longest forms of wavelength. And so the yellow part here is the radiation that is being emanated from the sun that goes towards the atmosphere. And the red part over here is actually the part of the radiation that is absorbed by the Earth's surface, or the radiation at the sea level. So you can see that from the yellow part and to the red part, there's a difference. That the space between these two are those that are absorbed by the atmosphere or reflected back towards the outside of the Earth. All right, so it means that not all of the solar flux that is coming from the sun, the radiation that is coming from the sun, are absorbed by the Earth. So some are actually reflected back. Around 50% are absorbed by the Earth. So if you average the solar flux that is being absorbed by the Earth, is around 1 kilowatt per square meter, or 1,000 watts per square meter. The total flux that is actually entering the Earth is around 1.37 kilowatts. So around 0.37 is actually absorbed or reflected back. So before we continue about the various mechanisms and how to harness energy coming from the sun, we try to understand first some of the terms that we use here. So solar radiation is the energy, the form of energy, the radiant energy from the sun, and this radiation can be measured in terms of irradiance or flux and solar insolation. So when we say irradiance, solar irradiance here is basically the instantaneous measurement of the power. So it means at a specific time. So when we say at 12 noon, the solar irradiance is around 1,000 watts per square meter. So this is the amount of power emanated by or absorbed by the Earth at that point in time. When we say solar insolation, it's more of a cumulative solar energy measurement. So it means that throughout the year, for example, the solar insolation throughout the year, including those times that there is no sun shining. So like the nighttime or the cloudy days, and also together with the time where the sun is shining, we can calculate all of this time and then and make it as an average. So the average solar insolation on Earth for a year is around 168 watts per square meter, or around 170 watts per square meter. So this is, if you look at this comparison with the solar flux average, which is around 1,000 kilowatts or 1,000 watts per square meter. This is basically the instantaneous irradiance at that particular time, especially at daytime. But the solar insolation takes into account even those the time that the sun is not shining. So throughout the night, as well as those times where there are cloudy days, for example, and your location. So on average, throughout the Earth, throughout the globe, so if you look at the circumference, the surface area of the Earth, based on the amount of power that is incoming from the sun, the average insolation is only 168 watts per square meter. But sometimes if we look at these two terms, irradiance or flux, and solar insolation, both can be actually used in the same way. So sometimes insolation can be in the same unit of watts per square meter, and irradiance also watts per square meter. So there will be more discussion on how to calculate the average solar insolation in the next few slides. So the amount of solar insolation, or the amount of solar energy that is being received by the Earth, will basically depend on the time of the day as well as on the location or where you are. So if you look at, for this example in this diagram here, so of course if the sun is shining directly towards you at the equator, so this part here has a shorter distance, as well as the area is quite concentrated. So you will expect a really high penetration of solar energy here. So you will have around 2.5 times more energy of this part here compared to the one at the poles, or the north and south poles. Because as you can see, if you look at from this side over here, when the sun is shining on these parts, it means that the area is now bigger. So it means in terms of watts per square meter area, so it means that the area is bigger now, so it has expanding. So it means that a smaller amount of energy is being received by this particular time. As well as if you look at the thickness of the atmosphere from this side here, it will actually probably go farther. So it means thicker thickness of atmosphere, and the atmosphere, as I mentioned earlier, will also absorb some of this solar energy. So if you look at from this side here, so it's a longer time, the thickness is higher. So it means there will be colder part in this area here compared to the one that is at the direct flux, or the direct direction of the sun. So this part over here. And of course, if you compare, of course, the different times of the day, as we all know, the part where the 12 noon, or the noon time, is where the sun is shining really high on the top of the earth. So it means that in the generation of, or the production of energy coming from the sun, so this part here around 9 to around 4 is where 90% of the energy can be generated. And so if that's also the same way, if you compare here, there's the same graph here. We can say that the peak sunshine hours is around 1,000 watts per square meter, but it's not always the case. We know that there are a lot of cloudy days as well, so it is the ideal case. But in most cases, the curve is like this. So you receive around 800 watts, around more than 800 watts per square meter of energy at that particular time. Of course, at evening sun, of course, if it is evening, the sun will not be shining at your part. But if it's an evening sun at the various locations around the world, it will also affect the amount of energy that is penetrating the Earth. So we try to calculate, or we try to understand how much is the average solar insolation on Earth. And in order to do this, we need to understand how much is the solar constant, that's emitting from the sun. So the power output from the sun is actually around 4 times 10 to the 26 watts of power, of total power. But the flux that is coming towards the Earth, or the solar constant, as we say, the solar irradiation. The average one is around 1.37 kilowatts per square meter, as I mentioned earlier. And so we can calculate based on the solar constant, which is around this value, times the area of the Earth that is receiving. So look at the sun, for example. If we have a sun here and it's shining towards the Earth, so it means that this part of the Earth here is receiving that part of the sunlight. So we are looking at the cross section. So the cross section of this part here is actually this part. So the sun is actually coming from perpendicular to this part. So the area of that is around pi r squared, or pi d squared over 4. So we can calculate the area of the Earth, indirectly perpendicular to the sun. So that means that is pi r squared, which is this is the radius of the Earth, which is 6.3 times 10 to the 6 meters. So we can calculate that one. So we can cancel the area here. We can generate around 1.73 times 10 to the 17 watts of power coming from the sun. So this is the power that is being received by the Earth. But as we can see from the Earth's energy budget from the sun, not all of the incoming solar energy or solar power is actually absorbed by the Earth. So many of these are reflected back towards the outside of the Earth. So these are reflected by the atmosphere, or some are absorbed by some of the particles in the atmosphere, are reflected by the clouds, and also reflected by the Earth's surface. So around 50% is being absorbed by the Earth's atmosphere. So from here, we can also calculate how much is the total incident radiation throughout the Earth by considering about 50% being absorbed of the total power that is incoming from the sun. So if we, as I mentioned earlier here, the solar power going towards the Earth is around 1.73 times 10 to the 17. So we can put it here, 1.73. And half of this is actually being absorbed by the Earth. So we can say that half, 0.5, versus 1/2 is absorbed. And then we can calculate the overall in terms of the flux in all of the Earth. So all of the Earth is actually the circumference or the area of the sphere of the Earth. So what is the area of a sphere? The whole of the surface area. So the surface area of the Earth is around 4 pi r squared, right? So 4 pi r squared. So this is the surface area of the Earth. So from here, the radius of the Earth is 6.37 times 10 to the 6 times squared times 4 pi. So we can have around 168 watts per square meter of average solar insolation on Earth. So this solar insolation, or the average solar insolation on Earth, takes into account those even those the time that the sun is not shining. So it considers during the time that there's a nighttime as well as daytime. All right. So it's not only considering the time where during the daytime, because during the daytime we have the maximum solar peak flux, which is around 1,000 watts per square meter. But if we try to consider the average one throughout the Earth, of course, it depends on your location and the cloudiness of or the situation during the day. But on average, it's around 168 watts per square meter. So the amount of solar energy that a specific place is receiving will depend also where you are. And we're fortunate enough that in Australia, we have a huge amount of solar energy or solar flux coming in. And if it's for comparison purposes, for in terms of UK, for example, at the northern part, and Australia at the southern part, the Australian is around 2.2 times higher in terms of the solar irradiance. So around 1,000 kilowatt hour per square meter per year for UK, and around 2,200 kilowatt hour per square meter per year for Australia. So this goes to show that there's a very big opportunity for Australia to actually try to harness many of these renewable energy based on the sunlight, and try to maximize this one for a potential big contribution in the sustainable energy future. So knowing the average flux as well the insolation that the world is actually receiving, but even so, it only requires around 0.14% of the total insolation from the sun that will be able to actually power all of the world's needs in terms of energy. And so we receive a vast amount of solar energy that it around